Hi guys, you're welcome to my channel. All right, today we're going to discuss about electrical design and drafting. Okay, it's a kind of it's also a continuation of our previous exercise where we study color coding and changes that have been made since 2008 concerning our regulatory body stipulated laws. The voltage changes and the color code changes and so on. This is a continuation of that because I discussed about design and drafting as well. Okay, we are not trying to also deviate from the subject of our channel. Our channel remains automation and control system update, where I will discuss about automation and discuss about control system. I give you update. All right, but because I have design and drafting in my training list, so some of our followers are trying to make a request for them to know what does design and drafting entails. That I should give them a brief outline on what they are expecting to get while going into design and drafting career. As an engineer, you should be able to know how to design, of course. Um, so don't think we are trying to leave automation and control. We are still there. It's just for me to make a clarification for those people demanding for this particular information. Okay, because of that, I've also put up a small miniaturized design, that is highway lighting system, so that we design this. Then from here we now know what and what that is obtainable in a design space. Okay, all right. I also recommended some design books that you have to get. you know like I always advise, you should have a hard copy information correspondent. Whenever you need information, you can always go and make reference to your design books. So it's always important for you to get design books if you want to go into design career. So design is all about your ability to understand project design, especially electrical design. So you should be able to know your load characteristics that you want to design. You should be able to know your supply characteristics, which type of voltage are you using for design, and what are the load that you want to design the project for. You have different types of load. Should be able to also know your installation outline, distribution system, standard final circuit, isolation switches, final assessment, compliance of regulatory body stipulated laws. So these are the things you need to go. Know your voltage drop, know your current carrying capacity of a given design, and know your low voltage and high voltage and the medium voltage and limitations of applying different variables and standard. Okay, so for instance, someone now, I give you little concept about this design. For instance, as an architect, you finish designing a building. What you're expected to do is to move that particular design, the soft copy, to an electrical engineer. What are you expected to do with electrical engineer? Electrical engineer is expected to put that same design into your system and now start designing the lighting load, the power load, the cable size, the voltage drop, the MCB rating, transformer sizes, generator sizes, and do your load distribution, your load segregation, and all whatnot. So that is what electrical engineer would do. After designing that, you now move the design back to an architect to do the further verifications and the approving, send to approve body for them to go through it. Then finally, you now approve it for printing. You now take it to your client, okay, or to go and defend the project for wherever it's coming from. All right. Okay, so that is all about design and drafting. Design and drafting is for you to design electrical project. Okay, that is design and drafting relating to electrical is what I'm talking about. Our electrical design and drafting is for you to prepare a project, put it in a hard copy, and then now go to the site and implement what is on the blueprint. That is design and drafting. Okay, some people will design, they will not supervise, they will give to another engineer to supervise. Some people will design and also supervise depending on the terms of agreement of the job. Okay, all right, so I just put up this for us to go through it. Then we use this one to show you some basic design concept and the approach. All right. As a beginner in a design and drafting career, you'll be working with predetermined factors. Predetermined factors are those factors you find in a table. In a table. So, like for example, you want to see the cable size, you want to get a cable size that can carry a particular current rating. You go to a table, you see list of cable sizes. You now choose the one that can carry that particular current that you calculated. So that is what I mean by predetermined factors. So you'll be working with factors that are already set aside for you to use. So you use it as a beginner, you are going to be using table for your design. Then subsequently, you will now do away with the table. You'll be working with your head because the formulas will be on your fingertips. All you need to do just put up the formula and get your figure. So you won't be needing the table as you progress. But as a beginner, you must need table. So I will show you two tables that you're going to use to complete this design sequence. Okay. Let me show you table one. This is our current carrying capacity. We are going to use this table, okay, to determine our cable size for our current, all right, our design current, okay. So we are also going to use this other second table to determine our voltage drop or for the selected current carrying capacity, okay. Okay, now let's start the process now. Now, I just put up this narrative to guide us. I said, okay, let us design lighting illumination system for 500 meters road distance with the following elements. So we're going to design lighting system for the distance of 500 meters, that is half a kilometer. So the lighting system is going to be a discharge type. This is a discharge fitting. There is flood light. Discharge fitting, they are the type of light that does not start directly. You know, we have to incorporate capacitor, incorporate ignitor, incorporate a transformer being the shock. Okay, so these three things, these three devices will be integrated inside the fitting. So that is discharge lighting, and that discharge lighting is a kind of the pressure in illuminating. It has the ability to illuminating a greater coverage of a space. So it has a pressure to light up a certain area better than direct. Okay, so that is why most people prefer this discharge lightings. All right, but the disadvantage is that the energy consumption is there. All right, so we're going to use it for our basic design. So we're going to also incorporate a photo cell so that at night the light comes up. Then in the morning, depending on your setting, after 6 or to 7, then the light will go off. All right. Now we are going to go through small little calculation, our process of a basic design concept. Okay. So now we are given these two things that the lighting system is going to be discharged and the rating of each of the fitting is going to be 250 watts. Then we're going to incorporate photo cell and the distance coverage is going to be 500 meters. So it's going to be a dual carriage road. You know that highways normally dual carriage going and coming back. So we're going to have these fittings two in one pole. Each of the pole will contain two of these 250 watts. So one face this other side, one face left, one face right. Okay. So that is why we are using 250 watts and two per pole. So we're going to determine this. Let's do that in a quick summary. Number of pole that we need, you have to determine this yourself. The end user has given you this information that the distance is 500 meters and the lamp it require is 250 and you need it to be automatic, that is photo cell incorporation. So that is what you need only from the client. The rest is what you're going to generate by yourself as a designer, right? Now let's go and generate that. We have given two, three informations. So let's work with those informations. One, number of poles to inert. You have to determine that. How do we know that? 500 meters is what we are given as a distance coverage. So how do we go? Now, because we are not giving the illumination rating, you know, every lighting system fittings have their illuminating strength. Okay, that is the rate at which you now cover the brightness. That is the illuminate system. We don't know, we don't want to go into that because the process is not for basic drafters. Okay, so because we are not given that size, so we want to be on a safer side to use. We're going to use 25 meters for each pole. Okay, because we don't know the rating of this strength of this brightness coverage. So we're going to use 25 meters for each pole. From one pole to another, we're going to choose 25-meter distance. So because of that, and we are told, we have also agreed that we're going to use two fittings for each pole. So in that case, number of pole here, we are going to determine it by putting up, let's get a calculator. Um, okay, let's put up a number of pole here. Okay, don't worry. Let's go to, okay, now we have 500 meters. We want to know number of pole to be used. Okay, so we have 500 meters. So if we're going to use 25-meter distance for each pole, we're going to say divided by 25. So we have 20 poles. Okay, like I said, let's use 25. Okay, so we're going to put 20 poles here. So we need 20 poles within the coverage of 500 meters. The number of fittings, I said each pole should take two fittings. So we are putting 40. Okay, then supply. What supply are we using? What voltage supply are we using? Okay, uh, we are going to, before we do that, we are going to, before we determine our voltage range, our supply characteristics. So let's work on this. Before we determine this, let's first of all know our load demand. What is our load demand? This is 250. Okay, so let's use another page to make the calculation a brief sum. I have 250 watts. It's going to be multiplied by 40. So what I have here is going to be 10,000. 10,000 watts. So let's do that. 250 watt for each fitting multiplied by 40 fittings. I have 10,000 watts. So if I have 10,000 watts, if I have 10,000 watts, so we are going to be multiplying that for every discharge lightings. Like I said, discharge lightings are those type of light that uses igniter. Um, uh, Let me mention some of them so that you know. Energy saving light is under discharge lighting. Your ceiling fan is under discharge lighting. Your fluorescent is under discharge lighting. Okay. Then your LED is still under discharge lighting. Any lighting system that uses capacitor, igniter, inductance, they are falling under discharge lighting. Then filament lightings is not a discharge lighting. That one is the starting current is the same with running current. So that one does not fall in the categories of discharge lightings. So, but those type of lighting system that has capacitor, igniter, and the show, and those interfacing devices, that means the light does not come up directly, it come up indirectly. It come up in addition, in aid with other devices. Okay. All right, now we are going to have a factor set aside, a factor of 1.8. That is a standard factor set aside to augment the starting current of any discharge lighting system. So we have a factor of 1.8. Take note, this is our wattage. Remember, this is what we have as our power demand. Okay, we have 10,000 watts. So we want to know the current rating of that system, of this entire system. So in that case, we're going to determine our IB. So our IB is going to be equal to 10,000, 10,000 multiplied by that factor I told you about, 1.8. Then now further divide by 400 volts. That is the declared voltage you are using. Why did I use 400 volts? Because the distance is 500 meters. So single phase of 230 will not survive voltage drop within this distance. So because of that, we are going to use 400 volts. I repeat, We choose 400 volts for the design because 230 volts will not survive voltage drop at the considerable distance of 500 meters. So that is the reason why we're using 400 volts. Okay. All right. Remember, I said as a beginner, you're going to work with predetermined factors. You're not expected to generate factors or know the formula to do your factors calculation. Now, you're going to be working with tables. Okay. All right. Now, this is what we use. Determine this. Let's bring a calculator and generate our IB. So we have this. We're going to say 10,000 watt multiplied by a factor of 1.8 that I told you we use for augmenting the starting current. So what we have is 18,000. Now divide it by the declared voltage you are working with. So I'm dividing it with my 400 volts. So what I have now is 45 amps. Okay, so come back to your design page. Now what I need, my supply voltage, we have agreed that you're going to use 400 volts. You know the circumstances surrounding using 400 volts. Then our current rating, we have also resolved that it is 45 amps. By calculation, we just did the calculation now, recover 45 amps. Okay, now the main circuit cable. Okay, the mains circuit cable sizing. How do we know our cable that can carry this particular current IB? How do we know the cable size that can carry this at a considerable distance of 500 meters? Okay. Then another thing, if you watch the previous exercise, I told you that we have 5%. I told you that we have 5%, sorry, set aside for power circuit, 5%. Okay, this is for voltage, permissible voltage drop, acceptable voltage drop for power circuit. They say 5%. So in that case, we are working with 380. That is the minimum. That is the maximum. We don't go below. So our declared 400 volts shouldn't drop more than 5%. In that case, it shouldn't drop more than 380. Because if we subtract, let's do that now. Let's do that. So since we are giving voltage drop limitation to be 5%, so and our declared voltage is 400. 400 divided by 100, this is what I have, times 5. So we are having 20 volts. That is our limitation now. So don't go higher than 20 volts voltage drop. So in that case, our 400 now, sorry, our 400 now minus 20 is going to be 380. So sorry, minus 20. So we are having 380 left. So our voltage shouldn't drop more than 380. Okay. All right. So because of that, we are going to factor another calculation process that is going to guide us on voltage drop limitation. So how do we now do that? Let's go. Before we determine this cable size, let's find out which cable size we take 45 amps over a considerable distance of 500 meters. So let's work on that table I told you you'll be working with. Let's quickly work with this. Okay, this is a table for current carrying capacity and for also let's first of all go for this table. Now this is current carrying capacity table. Okay, now this column is your cable sizes. Then from this column to this end of this column, there are the current of different ranges. Now the method of installation is what you choose above here. If the cable is going to be concealed and also buried in the ground or buried in the wall, you choose this method, that is reference A. Then if the cable is going to be concealed, it's going to pass through conduit, but trunking method, you choose this level, you choose this two column. Then if the cable is going to be clipped direct, you choose this one. If you're going to be free on air without concealing, without passing any distress of pipe, whatever, just free on air, you choose this one. So any of this one, these are the conditions of cable routing you want to choose. Then here now are the cable in parallel. How many number of cable you want to go? How many cable in parallel? This one say, is it two cable in parallel you are working with? Then take the current here. This one said 3 to 4 cable in parallel you are working. Now take from here. In the case of our own example, we are working with armored cable. So we are working with um, 4 core cable. So because of 4 core cable, we are taking from here. We are taking our current from here. So now choose your 45 cable, your 45 amps. So come here, check your 45. I don't have 45, I have 39. I don't have 39. I don't have 40. The next one I have is 52. And we are working with 45. Take note. So because I have 39 and the next is 52, so I'm choosing 52. So trace 52 to where you have cable size. It fall on 16. Definitely you can quite agree with me that 16 square cannot convert 45 amps current over the distance of 500 meters. You know you cannot go. But I want us to prove that by calculation. If I tell you cannot go, I don't have evidence. If you also tell me that I cannot go, you don't have proof. So in that case, let's prove it by going to voltage drop calculation. So this is how to understand this table, how to plot the table and use this factor to do your design. Now let me go to another table where we have voltage drop table. Now this is our voltage drop table. The same condition I told you the other side is the same way you refer to this one. Which condition you want to install your cable, you choose the condition, you now choose the voltage drop factor below them. Now we are working with 16 find 16 here. Look at my 16 So which method are we using for 16 Method of concealing and conducting. So it fall on 2.8. So the factor, our voltage drop per meter here is 2.8. So we're going to use 2.8 to factor into our calculation process to find out voltage drop that we are going to recover under the 500 meters cable routine. All right, now come back here. Now, what is the formula for our voltage drop? Look at the formula here. The formula say voltage millivolts multiplied by current multiplied by meters, the distance of coverage. I repeat, the formula for voltage drop is millivolts because your voltage drop is normally under millivolts. So millivolts multiplied by current you are working with multiplied by distance coverage, that is the meter, is what we are doing. So in that case, let's factor in. You know we have 2.8. Now multiply 2.8 by your 45 amps you are working with. Then multiply again by 500 meters. Then divide the result by 1000. All right, pay attention now. Remember that 2.8 factor was the one we got from the table. That is the standard, a constant factor. This 1000 is also a constant factor. This 1000 is to enable us to divide the whole of this, convert it to millivolts. We are converting the whole of this from the voltage to millivolts. So we are getting millivolts. All right. That is, the voltage drop is going to be in millivolts range. So we are converting it by dividing by 1000. Now I repeat again, 2.8 was a factor gotten from table, a standard factor, a factor set aside for you to use. 45 here was the current we calculated for our IB, our design current we are working with. Then 500 here was the a given distance by the client. Look at it, 500 meters. We want to cover, light up 500-meter distance road. All right, so come back here. So you are aware of this. So get your calculator. Let's now determine voltage drop for that. Now we have 2.8 going to multiply by 45, further multiply by 500. What I have is this. Now divide it by 1000. What I have is 63 volts. Come back to your table, design table. The voltage drop say we have 63 volts. Meanwhile, the stipulated voltage for you to work with is 405 percent. So now I have 500. Let's do again. 500 divided by 100 is what I have times 5. We are given 20 volts. Okay, we are given 20 volts voltage drop as a permissible voltage drop. So 20 is what we recover, is what we are given to work with. You shouldn't go below 20 volts voltage drop. But our voltage just dropped 63. So C, that means 16 mm square cannot go. So go back to your table, choose another one. So come back here and choose another one. Now, without wasting our time, let's choose 70. All right, I don't want us to continue using another one to delay you. Let's choose 70. 70 fall under what? 70 mm square is what I've chosen for that design. So come back to voltage drop. What is our factor for voltage drop for 70? Look at the 70 mm square I have chosen. Look at the voltage drop factor for 70 mm. 0.72. 0.72. So we are going to factor that calculation again. Come here and change this one to 0.72. Then calculate again. Get your calculator. All right. So we have 0.72 multiplied by 45, further multiply by 500. This is what I got. Divide it by 1000. I have 16.2. So this one meet our requirement. Our requirement say 20 volts is our maximum voltage drop. But I have 16 point what? I have 16.2. Okay, so 70 mm square is sufficient to cover 500 meters. So in that case, come back here, come back to our cable size. Main cable size is going to be 70 mm square. So put 70 there. So we are using 70 mm square for our armored cable for our routing, cable routing. Now the next again now is for us to determine our branch circuit cable. Our branch circuit cable. Okay. All right. But before we do that, let's determine our incomer breaker, our IN. Let's determine our IN. Okay. All right. Don't worry. Let's go sequentially. Branch circuit said, I said we're going to use 2 light fittings for each pole. So, and the one is giving us by 250 watt for each lamp. Divide by multiply by 2. We are using 2 lamp in one pole, 2 fittings in one pole. So one pole is going to produce 500 watt. That is the power of our one pole, power demand for each pole. So now we want to determine the current of each pole so that we know the MCB for our branch circuit. All right, go back to our calculation table. So we are going to say our branch circuit, um, MCB, MCB rating going to be equal to branch circuit MCB rating going to be equal to 500 multiplied by a factor. Remember, it's discharge lighting, a factor of 1.8, then divide by 230. Remember, we are using 230 for each pole. Come back again to avoid confusion. This is pole. This is number of pole, 20 pieces. Each of the pole is going to contain 2 fittings, and those 2 fittings, the rating of each of the lamp is 250. So this 250 will be times 2 of the fittings. So for the pole, you're going to form a catapult. One of the light fittings face right, one of the another light fitting face left. So both of them, the rating of both of them is going to be 500 watt. Okay, 500 watt for 2 of them. All right, it's okay. So 2 of them now is 500 watt. We want to determine the current, the rating of the MCB to protect the 500 watt for each pole. So that is what we are doing now. Okay. So come back now, say 500 times 1.8. You know, it's the charge lighting. This is a factor standard set aside is a constant factor. Now we are working with 230 single phase. Okay, that is why we choose 230. So get a calculator. We now say, okay, we have 500. We have 500 multiplied by 1.8. This is what I have. Divide it by your 230 volts. I have 3.9 amps, approximately 4 amps. But this rating is not available in the market, but we have 5 amps. So our branch circuit is going to be 5 amps. Okay. All right. Now our incomer breaker sizing. IN. You remember we determine IB as our design current. Now this is IN. IN is our protected device rating. Now there is also a factor set aside, a factor of 1.45. A factor of 1.5 amps is set aside to augment starting current of starting strength of this your circuit. Okay, so for you to have your IN is going to be, for you to determine your IB is going to be multiplied by 1.45 to get your IN. For you to determine the rating of your IN, that is the protected device size, you are going to multiply IB, that is your design current, multiply it by 1.45 for you to get IN. This factor is set aside because sometimes this IN can withstand your IB in a instantaneous condition. Example now, I have 5 load put together, and those 5 load come up one after the other whenever I energize this IN. Then in some instant, all of them will come up instantaneously. So for this breaker to be able to withstand that simultaneous engagement, you should be able to augment the strength, the size of this to come up to be able to carry your IB if they are coming up instantaneously. Some systems are designed for this IB to come up one after the other. There is total. Before the IB will complete, this sub-circuit will come up one after the other. Some situation, they will come up instantaneously, simultaneously. Okay, so that is why we have to increase this electrode to be able to carry. And because you know that before each of the branch circuit will come up, all of them have their starting current, which we have added by adding 1.8. But that 1.8 is not just for the charge lighting. It also affects the IN, the incomer. When each of the branch circuit is coming up, the current impact, the impact is coming down to IN. So this one is going to receive the impact that each branch circuit is coming up with a certain range of current. So this one is going to receive the impact as well. So having gone through 1.8 by augmenting this by adding branch circuit starting current, the strength and the energy is still bounce back to IN, to the incomer breaker. So that is why you have to also augment this a little. Take note, do not add IN, do not increase the size of IN, because in terms of fault, it might not trip on time if you further increase it more than this. Because before the regulatory body set aside this, they have tested different factors and find out that this one is most suitable. They have tested different factors and decided that this one is the most suitable. That is why they have chosen this factor for us to augment this. Remember that this is not just only factor for augmenting a protective device. This is because we are doing a certain design. different categories of design, we have different factors to work with. But why we are working with this factor is because this factor is the factor stipulated layout for us to use for this category of design. Please, you are going to take note of this, okay? All right. If that is taken, then take away this. Uh, okay, so we have determined this to be Brine circuit MCB 5 amps. Okay, this one. Okay, okay, take away this now. We have done this before. Take away this. Okay, then this one is contactor. Okay, so we have done this. Our incoming breaker, we decided to say, okay, let's finish it off. Sorry. We are yet to do that. So now let's just say our incoming. So we say that IN is equal to IB multiplied by 1.8. Okay, so in that case, what we're going to do is we have our IB to be 45. So 45 now multiplied by 1.8. So come back here and get your calculator. We have 45 as our IB multiplied by 1.8. We have 81. We have 81. So come back here. All right. Now, as you come back here, now we are going to have our incoming breaker here, MCB, to be 81. So we don't have 81, but we have 80 amps. We have to use 80 amps for our incoming breaker. Okay. All right. Then the cable size is 70 mm square. Right. Take note. And the 70 mm square against 80 amps, this segregation is enough for us to the trippage of this particular breaker. This cable, the temperature of this cable is more than sufficient to respond to the fault of this. There's another calculation for us to know if this cable size will respond to this one faster at how many seconds. Okay, that is a different approach. Okay, but I'm just giving you a kind of free hand sketch and reasoning. So this is 70 mm square and this is 80 amps. So these two sides, okay, you may not understand this until you do about 2, 3, so that you know the ranges of MCB and ranges of cable. If they are not close, you will know that this cable temperature, this cable cannot give rise to a certain temperature that can respond to this fault. Okay, okay. As you progress, you know better. All right, now contactor sizing. Contactor is not a protective device. There is a formula we use to pick, we use for sizing contactors. When we are doing control, when we are doing industrial motor control, there's a formula we use. But because we are not doing that, so we are going to do freehand selection for this contactor. Okay. So if my MCB here sizing is 80 amps, so you are also going to use that same 80 amps. The same formula you use to augment to get this one is also is going to take that. Okay, so but unfortunately we don't have 80 amps in contactor ratings, but we have 70. Okay, because of that we don't have 80, so we're not going to have back, sorry, we're going to take 100. Now 80 amps is our MCB by calculation. Now, and we don't have 80 amps in contactor rating, but we have 100. So that is why I've chosen 100. All right. Okay. The formula for contactor choosing will take your time. It's not part of this scope. Okay. All right. So we're going to use this one to feed our contactor. So we are done with voltage drop calculation. We are done with this. We are done with all of this. So the next step now is for us to, we have gotten 1, 2, 3. Okay. The next step now is for us to now do our, we have gotten main switch, cable size, branch circuit, incomer, contactor, voltage drop. current rating of this, voltage, number of this. Okay, we are done with this. So the next now is to go to our design software to see if we can, let's see if we can put up some simulation. We are going to use something like this to do our design. We're going to use symbol like this, or possibly if we can use something like this. But why I want us to put up the wiring concept, wiring method, is because I want us to uh, simulate, because we're going to use photo cell. All right, there's one other thing we omitted. We want to determine our size of cable for our branch circuit. Okay, this is this is actually our branch circuit cable size, not even current. Sorry. So the current, we need to insert it again. We need to insert our circuit MCB. Okay, branch circuit. Branch circuit MCB is 5 amps. We have gotten that already. So we're going to do branch circuit cable size. Okay, we have a 500 watt. We have 500 watt. So we are going to go back to the table, come back to current carrying capacity. Okay, so we are going to use 2.5. We can also use 1.5. Let's choose 1.5 mm squared. All right, because 1 mm you may not get a solid one there. So let's say we need 1.5. We're going to use 1.5. Our branch circle is going to be 1.5 mm squared. 1.5 by 3 core. It's going to be auto flex cable. Yeah, it's going to be auto flex. That is 3 in 1 auto flex cable. So live and neutral, that is live, neutral, and earth. That is why we are using 3 core. Okay, by 3 core. So that is what we are using. All right, now let's go and design the circuit. All right, we are done designing, we are done drafting. So we are trying to go to the wiring design, and from there we now simulate. Okay, all right.